In this video, I will discuss representation of electric fields by equipotential lines or surfaces, electric field between two charged parallel plates, and the analogy between electric field and gravitational fields. Another way to represent the electric field in a region is through lines or surfaces of equipotential. An equipotential surface is a surface on which every point has the same potential. So the magnitude of the electric field is dV dr. Hence, the closer the equipotential lines or surfaces are to each other, the greater the change in potential for the same distance, and hence the stronger the electric field. The direction of the electric field points from higher potential to lower potential. Electric field lines are always perpendicular to equipotential surfaces. Okay, why electric field lines are always perpendicular to equipotential surfaces? Equipotential means same potential. In other words, the potential difference between points on the equipotential surface is zero. Suppose the electric field line is not perpendicular to the equipotential surface. In this case, we can resolve the E field into a component that is perpendicular to the surface and a component that is parallel to the surface. If the component parallel to the surface is not zero, there will be a potential difference along the surface. So this contradicts the statement that the surface is equipotential. Equipotential means the potential difference is zero. Hence, E field lines are always perpendicular to equipotential surfaces. Okay, figure 18 shows some examples. Figure 18 shows some examples of equipotential surfaces for different systems. We usually draw these equipotential lines or surfaces the same number of volts apart. Okay, these are important diagrams. Please study them carefully. Okay, for the case of E, two parallel plates with opposite charge, okay, the lines will be parallel because it's a uniform field. Okay, for D, positively charged sphere and a negatively charged plate. Charges in equilibrium on conductors. An electrical conductor contains charges that are free to move. Hence, when a conductor is charged, the charges will always redistribute themselves until the excess charge resides on the surface. When the charges are no longer moving about, they have settled down in equilibrium, means they experience no net force. This implies that the electric field in the conductor is zero. Since the charges at the surface experience no force parallel to the surface, the electric field along the surface is zero. So we say that the surface of a conductor is an equipotential surface. The electric field lines emerging or ending on the conductor are perpendicular to the surface. So these two are important points when you're drawing electric field lines emerging from a conductor. So the potential in the conductor is constant everywhere inside the conductor and is equal to its value at the surface. So that means there's no field lines inside the conductor. So this example of a conductor inside an electric field. So on the left side, okay, the electric field in a neutral uncharged conductor placed in an external electric field is zero. The free electrons in the neutral conductor redistribute themselves such that the net electric field within the conductor is zero. One can imagine the separated charges within the conductor producing an internal electric field that balances the external field. Okay, these are the rules for drawing electric field lines and equipotential lines. Study them carefully. Electric field between two charged parallel plates. So the electric field in the space between the two plates is said to be uniform. So the magnitude of the electric field strength is V over D. This is an important equation and is only true for parallel plates. The direction of the electric field, E, is directed from the plate with the higher potential to the plate with the lower potential. Motion of charged particles in a uniform electric field. Uniform means the magnitude and direction of the field lines are the same. In other words, the field lines are parallel. So by Newton's second law, ma equal to QE, the acceleration is QE over m. Now, in most questions, the mass is so small, the electric force overwhelms the gravitational force. For example, if you are considering an electron, the weight is 8.94 times 10 to the power of minus 30 Newton. But the electric force is 1.6 times 10 to the power minus 18 Newton if the charges are separated 10 centimeters apart. and the potential difference is 1 volt. So you can see that the electric force is 10 to the power minus 18, but the gravitational force is 10 to the power minus 30. So it's 12 order of magnitude larger for the electric force. However, you should not assume that it's always the case that weight can be ignored. You might have a question where the mass is large enough to make the weight significant compared to the electric force. For example, the electric charges are inside an oil drop. So the motion is similar to a motion of a mass near the surface of the Earth. If the initial velocity is 0 or parallel to the direction of E, the charged particle will move in a straight line. If the initial velocity is inclined to the field, it will travel in a parabolic path, or we say projectile motion. Example 8. A beam of electrons traveling at 1.35 times 10 to the power 7 meter per second enters a uniform electric field between two plates of length 0.060 meter, which are separated by a distance of 0.020 meter. The top plate is plus 50 volts while the lower plate is minus 50 volts. Find the angular diffraction of the beam as electrons emerge from between the plates. So the horizontal speed of the electrons remains the same throughout. A constant upward electric force acts on the electrons as they travel in the region between the plates. So you can find the force, which is 8 times 10 to the power minus 16 Newton. So from there, we can find the acceleration. So we can find the time. The time is given by the x component. The distance is 0.060 and the speed is 1.35 10 to the power 7. So we get the time is spent inside the plate. So from here, we can get the y component of the velocity, and hence we can calculate the angle of diffraction. Analogy between electric fields and gravitational field. So you can see that there's a lot of similarity. So electric field strength is F over Q, gravitational field strength is F over M. So once you understand the difference and similarity between these two, you will be able to find similarities in this interaction as well as this motion. So study this table carefully. Okay, we've come to the end of section 12.5, 12.6, and 12.7.